Hello, so my name is Maureen. I'm actually an engineer in the search quality group, and so I'm introducing Professor Vincent Blondel from the Université Catholique de Louvain in Belgium. So he's a professor of applied mathematics at UCL, and he's also the head of the Department of Mathematical Engineering over there. And he was my thesis advisor when I was an undergrad student in Belgium. He's also currently doing a sabbatical year at MIT. And today's talk is going to be about a new concept of similarity measure between nodes in graph, and is going to talk about different applications such as the web graph, but also some telecommunication networks, and also synonym generation from graph of synonyms.
So can you hear me? Do I need a microphone? Can you hear me in the back?
Yes? You will. Good try.
Okay. Very well. So thank you. I'm very happy to be here for this talk. I apologize for the rescheduling of the talk. I initially planned at this morning at 11, and my flight from Boston yesterday was cancelled, and so I arrived only this morning. And I'm very happy to be here, even though it's raining. The temperature in Boston when I left was about 0 degrees when I left, so I'm happy to have an increase in temperature. So as Maureen said, I'm going to talk about similarity in graphs and networks, and let me directly illustrate what type of tools I'd like to present. And the tool I'm going to present appeared in a paper which has Maureen as a co-author in Science Review 2 years ago. So the tool I want to describe is a way of expressing how similar nodes are in graph. And here is a very little example. You have a first graph, graph A here, and you have another graph B here. And then from these two graphs, we construct a matrix that expresses how similar these nodes, the nodes in the respective graphs are. Okay, so the matrix has as many columns as there are nodes here, and as many rows as there are nodes here. And if you look at the entries of the matrix, these entries are attempts at characterizing how similar nodes are in these respective graphs. So for example, so this is what we intend to do in this similarity matrix. And so for example, if you take node 4 here and node 5 here, so you take the fourth column and the fifth row, you get a 0, which means essentially that this node here doesn't at all look like this node here. If you look at the largest entry in this matrix, the largest entry is in here, and this entry corresponds to node 3 here and node 4 there. And so this entry says that indeed node 3 in the graph B looks very much like a node 4 in graph A. Okay, so what I'm going to do during this talk here is to explain how we can derive this similarity matrix. I'm sorry, this microphone is just going on and off. Is that should I keep using the microphone or? Oh, can you hear me well with the microphone? Okay, very well. I'll continue with the microphone then. Okay. So what I'm going to do during the talk is describing the way we construct this matrix. And the matrix is very inexpensive to compute. It's very cheap to compute, and so it can be computed on very large graphs. I haven't represented here very large graphs, but it can be constructed for graphs that have millions or more nodes. And typically, one possible application is a situation where we have one little graph that expresses some structure that we'd like to extract from the large graph. Okay, but other potential applications are when both graphs are equal, in which case what we do is essentially characterizing how similar nodes in the same graphs are. Okay, so we just then have one graph and we try to express how similar nodes are in these graphs. So here is another illustration of the matrix. You can, of course, choose one particular node in the first or the second graph, which corresponds to picking either a row or a column, and then ask which node is most similar in the other graph. So for example, here, if we choose node 4, it means that we choose the 4th line, And in the fourth line, you're asking which is the entry that is large, which is the largest entry. This is the largest entry. It corresponds to column 3, which means that the node here that is most similar to this one here is node 3. Okay? So this similarity matrix is a useful way of characterizing similarities between nodes in graphs. And as I said, it's easy. I'll describe it during this talk. It's easy and inexpensive to compute. The cost is linear in the number of edges, so you may have very large graphs. And it can extend to a situation where we not only have graphs, but we have networks. So typically we have weights on the arcs. So if this corresponds to a website and this another one, maybe we have a weight on the arc that tells how many links there are. And if this is a cellular phone communications network, then probably this says how often this person here has called this other person there, and so on. So it extends to the situation of weighted graphs. So what I'm going to do during the talk is that I'll first describe how we came to that definition, which we came to by extending a notion that was introduced by John Kleinberg from Cornell, which is the HITS method, which I believe that most of you know, for searching the web, which is an alternative way to the PageRank computation. And then I'll describe how to extend this notion of HITS to computing similarity in graph networks, and then I'll go to a few applications. And as Maureen said, one of the applications will be automatic synonym extraction of monolingual dictionaries. And I'll describe some experiments we did on a dictionary. Okay, so the method of Kleinberg, as you can see this is a proof, not a mathematical proof, this is not a proof by simulation, it's a proof by Google Scholar, that it has attracted a lot of attention in the scientific community. Yes?
Can you back up to the very beginning? What is the motivation for considering that there'd be any similarity between a node in graph B and a node in graph A? They have nothing to do with each other, apparently, other than they're both round and they both are labeled with the same numbers.
Yes, so, but wouldn't you agree that this node here probably looks a little more like this one rather than this one here, right? So,
what characteristics are you judging similarity then?
Okay, so then what you're asking, I suppose, is what notion of similarity do you want to express in the similarity matrix? Is that your question, or what type of similarity? Okay, so there are many different ways of defining similarity. And this one here, contrary to the usual definition of similarity, usually similarity is defined typically in terms of the number of paths, or a weighted sum of number of paths that are between two nodes. And two nodes are said to be similar if they are sort of close to each other, or if the number of paths. Whereas here, the notion we capture with the similarity matrix is completely different from there, in the sense that the two nodes may be completely disconnected, and even though have a high degree of similarity. And the notion of similarity we capture is the one of the structural position of the node within the graph. So this node here has a structural position within the graph that is somewhat analogous to the structural position of this node in this other graph. And so that's the notion that we capture. So the notion is really not a measure of the weighted sum, or which are the usual notion of similarity in graphs, so a weighted sum of the number of paths, but the notion of the structural position of the node within the graph. So for example, if we look at communities, typically, and we have two different graphs that represent communities, perhaps that if we identify nodes that are similar in the two graphs, these nodes will represent people that have similar interconnection to other people. Okay, so although they are not related at all to each other, because they have no links, but they play the same role within their community. So that's the notion we want to express. Yes?
You say that the computing is linear in the number of edges.
Yes.
The output itself, if it's the similarity matrix, can be larger than the number of edges, the input graph. It can be the quadratic.
Well, yes, well, okay, so I shouldn't have phrased it this way. What I mean is that once you choose, typically I choose a graph here, which is a small graph, because I'd like to extract from a large graph. I'd like to extract features of that large graph that are expressed in the small graph that I have here. And then this computation is the number of edges I have in the large graph. Okay, but you're right. So if in full generality, if in particular if we have the same graph here and the graph there, then this is n square, and we need at least n square operation. Yes.
Is there a concise definition of similarity in terms of mathematical
Okay.
formula?
Yes. So I'll give the precise formula for this similarity matrix. Okay. So it's not like, I understand some of your questions, so it's not like we had an idea of what similarity we want to express and then we came up with a formula. So it's the other way around. So we extended this notion of Kleinberg and then we looked at what type of similarity it expresses. Okay, but I'll give a very precise formula for this. Okay, so let me come to first a quick description of Kleinberg's method, since our method is an extension of Kleinberg's method. So let me first describe Kleinberg's method. So the idea of Kleinberg was to assign to websites, to web pages, a measure of whether the web page is a good authority or whether it's a good hub. So if you type in a search word like University Belgium, then these pages would be good authorities because these are the home pages of different universities in Belgium. Okay, so these pages will have a very high authority score. Whereas this page here has a number of links to other Belgian universities, and so this page here will be perceived as a good hub. Okay? So the idea of Kleinberg was simply to assign to every page a score that is its hub score and a score that is a hub authority score. Okay, so every page has two scores, not just one, not just a page rank, but it has two scores, a hub score and an authority score. Now, when are you a good hub? You are a good hub if you're pointing to good authorities. And when are you a good authority? You are a good authority, you have a good authority score if pages that have a good hub scores are pointing to you. Okay, so it's just a circling definition. And he expresses the circling definition in this formalism here. So every page is given an authority score and a hub score, and web pages with high authority scores, if they are pointed by pages that have a high hub score, and the other way around. Okay, so how do you start and how do you pass the way that this is a circling definition? Well, one way of doing this is to just assign the same hub scores and authority scores to all pages at the start, and then start iterating this little linear update. So the linear update does what? Well, the hub score of page J, gets the sum of the authority scores of the pages J is pointing to. And then just the opposite for authority score. The authority score of page J is just the sum of the hub scores of the pages that are pointing to J. Okay? And so we start with an initial assignment of these hub and authority score, and then we iterate this. Of course, this will explode with time, because if we give an initial assignment of 1, this will just increase. But then at every step, we just rescale these two vectors. Okay? And if we do this, then what one can prove is that independently on what you started from in terms of initial score, this process always converges. And it converges to the same value that is independent from the initial assignments of the hub and authority scores. And it corresponds, these two values, these two vectors of hub scores and authority scores correspond to the eigenvector, the dominant eigenvector of, or the dominant dominant eigenvector of a matrix that is computed by just taking the adjacency matrix of the graph multiplied by its transpose. And the other one is the dominant eigenvector of the transpose multiplied by the matrix. So these are the singular vector of the adjacency matrix of the graph. Okay? So it's a very natural, and this is essentially the power method for computing eigenvectors. Okay, which is of course, a well-known way of approximating eigenvectors of linear transformations. Okay, so now what I'd like to do is to think, and that's just the innovation. I'd like to think of these hub scores and authority scores in some sense. What we want to express here is to assign scores, 2 scores to every web page, and these 2 scores correspond to a similarity to the hub or a similarity to the authority. And what I'm going to do next, and so Kleinberg methods express similarity between nodes in a graph with this node in this little graph and this node in this little graph. And what I'm going to do is just extend this idea and have here a graph that is more general than just the hyperauthority graph. Okay, a very natural thing to do. Let me do it just for a simple graph, a very simple graph with 3 nodes. So it's the simplest extension of this idea. So assume that we now have a begin node, a center node, and an end node. And we have this little graph here. And now I start again with my large graph. And to all nodes in my large graph, I'll now associate 3 values. Not just 2, hyperauthority, but 3 values. And these 3 values will correspond to whether the corresponding node is similar to a beginning node in this graph, a center node in this graph, or an end node in that graph. Okay? So this is a very simple idea. We just have now a 3-node graph. And we compute similarity to this 3-node graph. So how do we do the update? Well, what is my score? What is my beginning score? I have my beginning score of page J is high, provided I'm pointing to pages that have a high C score. Okay, exactly as we did for Kleinberg, we do something slightly more complex, but we update the value of J, the B value of J, the beginning score of page J, as the sum of the center score of the pages I'm pointing to. And similarly for the end score. And then for the center score, we take, of course, the value both of these guys and of these guys there. Okay? And then we update this transformation. It's again a linear transformation of the score. So if you take B, C, and E, and you look at how they evolved after just one iteration, it's just a linear transformation. And so for sure, we'll come up with another type of eigenvalue problem. And indeed, what the quantity that we're going to converge to with these scores is again an eigenvector, but of a matrix that is now constructed from the initial JCC matrix of the graph, but in a slightly more complex way as the one we had for the Kleinberg method. Okay? So here's a little example of a graph of which I've computed the similarity with this graph. And if you take, for example, the 2 node here, and you're looking in this graph and you're asking which, among all these nodes, which one is most similar to this node in this little graph? Well, it means corresponding to the corresponding column here. And what the method says is that this entry, the second and the third entries are those that are most similar, which means that the node 2 and the node 3 here are the 2 nodes that are most similar to the node 2 in this little graph. Okay? And we can prove as a property, which is analogous to the one we had for Kleinberg, that if you start from an adjacency matrix of the graph, then the central score, which by this I mean the score associated to this node, will be given by the dominant eigenvector of the matrix here, B transpose B plus B transpose B, where the B matrix is the adjacency matrix of the graph there. So maybe I can just yes. And if I now denote this in a more compact way, I can use B, C, and E just to put them in matrix form, so as to construct the similarity matrix. And then one can see that if you look at these iterates and you look at how B, C, and E are being updated, okay, then the question is, how is this matrix S, this similarity matrix S, how is this matrix being updated? Well, you can express the update of the matrix S in terms of the adjacency matrices of the large graph and of this little graph here. And now A is the adjacency matrix of the large graph, and B is the adjacency matrix of this little graph here. And if you look at the updates, updates are linear, and you can write them in matrix form in this way. So that what the method boils down to, and that's the only equation you have to remember in order to compute the similarity matrix. This is not, of course, writing the matrices is not the most efficient way of doing it. You should never write these matrices explicitly. But what the computations correspond to is just making this update. We start from some matrix S, which can be taken an arbitrary matrix, and typically we take a matrix with ones everywhere, and then we update this linear transformation and reconverge exactly as with the power method for eigenvalues, for eigenvectors, dominant eigenvector. Here we obtain a dominant eigenmatrix, And this is the S matrix is the eigenmatrix corresponding to this linear transformation. Okay. Now, the fact that we're using the JCC matrix, let me just give a quick reminder that the JCC matrix of a graph, well, I'm sorry, is a matrix that has its rows and columns corresponding to nodes and has a 0 and 1s depending on whether there is an edge between the corresponding nodes. Okay, so this is just a small. This is a matrix for a small portion of the World Wide Web, about 60,000 nodes, and as you can see, it's a highly structured. It's a highly structured matrix, which clearly shows that, of course, these matrices should never be computed explicitly because for most of the entries, these entries are 0. But going through them, we can see the apparent structure of the interrelation between the nodes. Okay, so now this is the updating equation, and I've motivated this updating equation for the particular situation where we have the BCE graph. And so the way this little graph appears in this formula is that it's one of the two JCC matrices appearing in this update. But there is no reason to limit ourselves to just graphs of this type, and the same formula, exactly the same formula, can be used for any type of graphs. And so this is one way of expressing similarity between nodes in graphs, and that's the updating equation I've used in order to produce the similarity matrices that I've shown at the beginning. Okay, so the algorithm for computing similarity is now very, very simple. We constructed the JCC matrices of A and B. We start with a matrix that has ones everywhere. We update, and we need to take the even in order to ensure convergence. We need to take the even iterates. We compute the even normalized iterates in the sense that after every step, we also need to normalize the matrix, divide it by its norm, and then after convergence, we stop and we obtain the similarity matrix, which is an eigen matrix associated to this linear transformation. Okay, so here is again the example I've shown before, and as I said also at the beginning, you can of course apply the technique by using here and there the same graph, in which case you obtain a matrix that expresses similarity between nodes within the graph. So here's the similarity matrix one obtains by starting with this graph and having the same graph to which we compare it. And as you can see, the results are rather convincing in the sense that what the method finds out is that these two nodes are which is of course the natural thing to do, that these two nodes are similar to each other, but there is no similarity between the other nodes, which corresponds to the fact that we have non-zero entries on the diagonal elements and the matrix there that express the similarity between 3 and 4. Okay. So let me briefly describe one first short application of this to the analysis that we did of a cellular phone network. This is a contract we have with a mobile phone company in Belgium, one of the major mobile phone company in Belgium. They have recorded complete data for 6 months period in 2005. And so, of course, Belgium is not that a large company, so we have 2 million customers, but it's large by a Belgium scale. So we have 2 million phone numbers, and they've formed about 600 million phone calls between these telephone numbers. And what cellular phone companies are interested in are typically questions like whether how the graph looks like, this graph or interconnection, how does it look like? Are there people who are likely to move to some other mobile phone company? Can I identify communities within that network? And typically, how will a new service or a new product spread in that community? And if I want to spread the product in that community, what should I do? Who should I give the product to? Where should I target the advertisement, and so forth? So they'd like to do viral marketing. Okay, so this is the distribution of calls received on this large graph. As you can see, some of these customers receive a very large number. So this is the number of calls received, number of customers on a log-log plot. And so there are some customers who have received more than 1,000 phone calls, but most of them here have received just one. This is a very large number of customers who just received just one. And you have this distribution of number of customers versus number of cores. And this is typically the type of graph you obtained in scale-free network. For a scale-free network, you have a line and a straight line here, which means that there is a power law distribution of these degrees. So this is just an attempt of verifying that indeed we have a scale-free network as we expect in the case of communication between cellular phone. And this is just a reminder that while the usual random network model for modeling the communication between cell phone networks is inappropriate, and it's more like a scale-free network, and these other type of networks also have this power law distribution of degrees. Then this is a representation of the graph of communication between all these nodes. And so in order to produce this, since we have 2 million nodes, of course we cannot even plot 2 million pixels on a computer screen. So we had to somehow identify leaders or main people in communities. And in order to do that, we used the notion of central score I presented just before in order to identify the person that we'd like to keep in order to make a representation of the graph. So it looks like the graph is separated in two parts. And after having obtained this, so we went back to the mobile phone company and we asked whether they had data about the language, because you may know that in Belgium we speak both French and Flemish, and whether they had information about the language, and they gave us this information. And so it came out very nicely. As you can see, you have this is Walloon, so it's these here speak French, these ones speak Flemish, and then you have the green ones are Brussels, because Brussels is sort of bilingual, it's in between Flemish and French, so it was a convincing argument that this representation of graphs represents something. Okay, so let me now describe another application, which is the one for automatic extraction of synonyms in a dictionary, and this will be the last application I'll describe. So in the dictionary graph, we consider a situation where the nodes are the words in the dictionary, and there is an edge U to V if V appears in the definition of U. Okay, so we construct a large graph, and this was the Webster dictionary that we took. And again, you can look at the in-degree distribution of the words. So some words have an in-degree of 1,000 or even almost 10,000, which means that they're used in 10,000 definition. And so these are the words of, the, and so forth that are used in many definitions. And so again, we have a scale-free network, which is the network we construct from that dictionary. So how to extract, automatically extract a synonym in that dictionary? So here's the method that we used, and I'll then describe the result we obtained. So assume we'd like to find a synonym to likely. So we have likely. We first look at the neighborhood graph. So we look at all the nodes that are used in the definition of likely, and we used all the words that use likely in their definition. So this defines a number of nodes, and we then look at the subgraph of the dictionary graph that correspond to these nodes. So we reconstruct the subgraph. So this is the subgraph reconstructed from likely. And this is a rather, well, we haven't represented all the words because there are more words here, but in order to this example to fit on the screen, we remove some of these. And if the graph is not large enough, then we may typically go one step more and look at the words that appear in the definition of the words that appear in the definition of the word. So we can take a diameter that is larger than we have here. And then once we've done this, we look at the similarity score of the nodes that are present in this graph with the central node in this little graph. Okay? So because of the way we've constructed this little graph, we've looked at all the nodes that we're pointing to, and we've looked at all the nodes that are pointing to us. Now, we expect the nodes that have a high central score to be good candidates for synonymy to our likely. Okay? And we use this to rank automatically synonyms. So here's the result that we get. And this is just an example for the word disappear. And we have 3 different methods here that do automatic synonym extraction. And these 2 are handmade synonym extraction. These are synonym dictionaries that have been handmade. And this is just the last but line here is just an estimate of how well the ranking was as evaluated by humans. Okay, so for disappear, the central method here is the one we've used. So this is the situation where we compute the central score of all the nodes that appear in the neighborhood graph, and we rank the nodes according to their central score. And as you can see, well, we have reasonable candidate for synonymy with our method, which clearly outperforms the other vector method and the arc rank method, which is essentially which is a method that was proposed by researchers at Stanford, and that is essentially an extension, well, an adaptation of the PageRank for the situation of extracting synonyms. Here's another word, science. And it's not quite clear what synonyms we could have for science. And again, as you can see, well, among the automatic extraction of synonyms, the central score is performing reasonably well. It doesn't perform very well as compared to the words that have the synonyms that have been composed manually by humans. But one drawback of our method is that it does not allow us to use composed words, which is allowed in human-made dictionary like knowledge domain, knowledge based, and field of study, which cannot be extracted from the central score in the way I've described it here. Okay, so the last word is sugar, and again we're performing reasonably well as compared to the other 2 methods. And as you can see, the handmade, the human-made dictionary of Microsoft seems to focus on a particular aspect of the word sugar. So we've had exchange with Le Petit Robert, which is the French dictionary, and they are now considering implementing this method in their CD-ROM version of their dictionary. Okay, so that's about the conclusion of my talk. So I've introduced a new notion of similarity, which is, as I said at the beginning, which has nothing to do with the number of paths between the nodes in the graph, but which expresses a more structured property of nodes in graphs. And this similarity matrix is very easy to compute. We just need to start with a matrix that has ones everywhere, and then iterate this updating equation, this normalized. We need to normalize, of course, but we compute normalized iteration of this equation. And so, which clearly shows also that the method is inexpensive, and so it can be applied to a very large graph and networks. Okay, thank you very much for your attention. Well, that's a good question. Well, these are adjacency matrices. They could as well have weights that correspond to the weights on the edges. Instead of having one, if you have several links, you just have a value that represents this. And it could be fractional values also. So, yes. Yes?
Since your computation, in the case of the 3 node, you compute the central score. Since you're essentially linear, you can get a good central score by either pointing to lots of end guys or coming from lots of beginning guys, and not both. Have you considered the nonlinear case where you essentially multiply those 2 things you sum together?
Or instead of taking the sum, we could take the product. That's what you. Okay, so in the central score, the way we define the central score is by. So if I can go back. So what you're saying is in these iterates here, we have a plus sign, we could have a product sign. Yeah, we could have a product sign, or we could have this quantity to, well, any norm, of course, of these 2. We could have some power here plus some power there, and all these types of updates are possible. The advantage of taking sums here is that we just then are in linear algebra, and we can prove convergence and all that. But it may be more relevant for application, but probably more difficult to prove than convergence, but more relevant for application to have something that is more sophisticated than just a plus. Yes, a product, for example, or something else, yes. Sure. But we didn't try that. Yes?
You mentioned the word convergence. What determines the rate of convergence for this?
Well, since this is just an iterate, this is the power method, so it's the vector will converge to the dominant eigenvector, and the rate of convergence will be given by the spectral gap, so which is essentially the distance between the first and the second eigenvalue of the matrix. Okay, so one would need to figure out what the second eigenvalue of this linear transformation is, depending on the size, depending on these two graphs. But that's what it is, right? So it's the second eigenvalue that will dictate the speed of convergence. In practice, after just a few iterations, we converge. That's what we've observed in practice. But any more questions? Yes?
How do you describe, or can you describe a scenario where the similarity is perfect between two nodes? Because you had an example where you had the similarity of the nodes in a graph with themselves, and yes. I didn't see any ones in that matrix. There was like 0.40 something. You had a similarity matrix that was.
Oh gosh, it's very long.
Yeah, I can't remember exactly.
So your question is, okay, here.
Yeah, that one. Yeah,
Yes.
I mean, why don't I see ones in the, what is a perfect similarity? I mean, why
Oh, the perfect similarity. Well, this is just a matter of, yeah, okay. So you're asking why do I have a 1 here?
What is a perfect similarity? Is this your
Yes, okay, so yes, it's a good point. So we've normalized, we compute the similarity only to be compared one to each other. So it's only the relative values of these entries that have to be considered. And so here we've taken a normalization where the sum of the squares of all values sum up to 1. But we could have normalized in a different way and we would have had 1s everywhere. Okay, so this is just the fact that, yeah, I suppose how many values do we have? We have 6. So if you take the square of this, it could be 1/6. Yeah, so it's just the scaling. But of course, similarity, the similarities coefficient that enter here should only be considered relative to each other. It's not never an absolute notion of similarity. Yes?
Each one of those power update only give your user like one column or one row, right? So it's similarity.
No. What you're saying that each of these iterates gives only one column or one row? No, this is the full, this S matrix has as many rows as there are nodes in the first graph and as many columns as there are nodes in the second graph. And so every iteration just typically updates all the entries of the matrix. It's a complete update of the entire matrix. It's not just one column. But maybe I didn't get your question correctly.
No, I guess that's the same thing, because essentially,
yes?
So this is finding similarities of individual nodes. Did you look at extending it to sort of finding the best match for the entire graph? So like if you flip back to the slide you were on before.
Yes.
Which one? The one that had the sort of the small simple graphs, this one.
Right.
So like how would you find the best match for all of graph A and graph B rather than the best match for a given single node?
Yes, okay, so that's a good question too, right? So how can we find a match of this into a large graph like that, for example, right? So there are intrinsic limitations of what can possibly be done, because if you're given a graph here which is isomorphic to another graph there, so it's just a renumbering of the nodes, then a perfect matching is possible. But deciding graph isomorphism is a problem for which there is no known polynomial time algorithm. Okay, so there is no way we going with such a simple technique solve the graph isomorphism problem. Okay, so it can only be up to some approximation. Yes, we're not going to solve that exact matching problem. But it will. So typically, if you take a graph here, and then you start with a little graph here, and then you sort of build a large graph around that one, and then you look at the similarity matrix. I expect that you'll find the coefficients, and by looking at the coefficient in the matrix, I expect that you'll be able to rediscover this little graph in the large graph you've constructed, but not in a completely systematic way, because that would be graph isomorphism. Yes.
Node 4 in the small graph looks like a hub, two things going out of it. It looks similar to node 2 in the larger graph.
Yes.
And yet, the graph doesn't show that at all.
Yes, it's not perfect. And of course, the example I've taken, I've tried to take the good examples on this matrix, right? But whatever you come up with, the notion of similarity is not a mathematical notion unless you define it very precisely. And so people have different notion of similarity. And for example, for you, it would sound like, and maybe for most of you, it would sound like you'd like to have a high similarity between 4 and 2, right? So which means taking 4 and 2. And in fact, it's not that bad, because this quantity, you should look in this corresponding column, right? So it's, excuse me? Oh, it's this one here. Yeah, it's not the best you can do. It's the third value. There are zeros there, but whatever you come with, if I was to come with another similarity measure, you'd be unsatisfied by some other relation probably. And so I'm not saying this notion is perfect, but it expresses some of the similarities between these graphs. If what you have in mind is counting the number of outgoing edges and incoming edges, then of course all of this can be thrown away, right? That's not what we have in mind. And probably then a very simple algorithm is possible if it's just a matter of counting whether they have identical number of incoming and outgoing edges. This captures something different. This captures something different. And of some interest probably for some applications. But it's not there are other notions of similarities, and this is just one of them, which is easy to compute and inexpensive to compute. Are there any other questions? Okay, thank you. Thank you for